So to illustrate this Bayesian framework, I have this picture which seems a bit frivolous, but it actually illustrates the challenges of inverse problems, of learning from data through models, actually quite well. You can imagine parameters. These cubes of meat here are parameters. The model is the body of the grinder. The outputs are the ground meat. And so the forward problem, which abstractly we can represent like this: M are model parameters, f of m means solve the forward problem given the model parameters to produce observables d. Well, this is obtained by turning the crank, solving the model, and you get these observables. So in many cases, the forward models are well posed. Not always. The famous examples where they're not, or at least the proofs are not available. Causal, and the operators are local. In contrast, the inverse problem is to go backwards. Take observations of the outputs and try to reconstruct the inputs. And you can see from this grinder that looks to be, in fact, almost hopeless. So the challenge really is that this going backwards from observables to parameters is often ill-posed. The observations are usually sparse, the forward operator is often smoothing, and as a result, many different parameter values may be consistent with the data. Okay, so how do we treat this? Well, there's a so-called classical approach that developed in, let's say, the 60s with the work of Tikhonov, and that is to employ regularization to penalize unwanted solution features and to guarantee uniqueness. And so the idea is to use optimization methods to minimize the misfit between the output of the model and the observables d in some norm, and to add a penalty, again in some norm, on the deviation of m from some reference value, which could be 0, but this is essentially a penalty on unwanted features of the model. It could be, we are penalizing the roughness of the model, we are penalizing the size, and so on. Okay, the alternative perspective is the Bayesian approach, in which we say, now hold on, we are interested actually in characterizing probabilistically all of the parameters, all of the models that are consistent with the data up to within the noise. And in the special case of Gaussian prior and likelihood, then one obtains an expression that looks like this, which is a posterior probability describing the probability of any model and its consistency with the data and with the model itself. So the expression that you get has some resemblance to this expression over here. Here we're minimizing a regularized data misfit. Over here we have a probability, a posterior probability, which is the solution of the Bayesian inverse problem, whose log has a similar structure, but it's interpreted differently. In particular, the regularization term is now replaced by a prior term. Cm inverse, Cm is the prior covariance. And so if, what we're saying effectively is that given observations, the probability of any particular model is related to how well the forward problem fits the data, but also how consistent we are with the prior knowledge. All right, so this is a much richer description of the inverse solution than this one. The problem is, though, that this gives us a probability density in very high dimensions. So the problems that we're interested often, well, they're infinite dimensional. We're trying to infer the initial conditions or boundary conditions or the material properties, the coefficient in the PDE, or the source term, or even the geometry. And when discretized, that gives you, well, a posterior distribution in 1,000,000 dimensions. And the second major difficulty is that this f of m is often a very expensive discretization of coupled nonlinear PDEs that runs on supercomputers that can take hours on many thousands of cores. So when you write a probability distribution the evaluation of which depends on the execution of this very complex model, and you're in high dimensions, now it becomes extremely hard to characterize this posterior, in particular to compute statistics such as mean and covariance. So actually, it's kind of ironic that we refer to the Tikhonov approach as the classical one that dates to the 1960s, whereas the Bayesian approach, can date to Bayes' theorem, 1763. But it's the challenges, the difficulty of doing this approach that has led to the Bayesian approach as really being the frontier. Okay, so what makes things difficult? I've already touched on this. So the Bayesian framework allows us to account for uncertainty in both data and models. But it's very difficult. It involves exploring high-dimensional space, which is very sparse. That's the curse of dimensionality. And when the uncertain parameters represent infinite dimensional fields, the number of parameters can number in the millions or even billions in contemporary problems that people are interested in, certainly in the geosciences. So these two complexities of high dimensions and expensive forward models essentially makes sort of vanilla application of Bayesian methods intractable for problems of interest. And conventional Markov chain Monte Carlo methods in particular become prohibitive for these kinds of problems. And that's probably why these techniques have not been employed to solve very complex problems in geosciences and other areas until recently. So some advances have been made, significant advances have been made, and I want to talk a little bit about those, give you a very high-level view of those. But what I also want to conclude with is that despite significant exploitation of the structure of the problem, it remains the case that you still need to solve many forward models, thousands, tens of thousands, hundreds of thousands, and this becomes expensive. And so the question is, can we look to machine learning to provide us with a way of constructing reduced order models that can then be evaluated rapidly. Now, these reduced order models have to be predictive, and they have to be predictive over very high dimensional space, so that's another big challenge for machine learning. Okay, I want to talk a little bit about some of the problems that we've been working on, just as an illustration of a much broader set of inverse problems that appear in the geosciences. This first problem has to do with global mantle convection. So mantle convection is how the Earth sheds heat. Heat in Earth's core and mantle rises buoyantly, and that leads to a flow of the rock. Very slow flow, takes a few hundred million years for a particular cycle, but the rock rises to the surface, it flows along the surface of the Earth, it cools, and then it descends. So you get these big convection cells inside the Earth, and this is what drives plate tectonics. So plate tectonics is the surface expression of this heat that's being generated and dissipated within the Earth. And so what you see here this is the Pacific plate, and this is a model of the motion of the plate. This is the flow on the surface. The model itself is a creeping flow. It's a nonlinear Stokes equation. It's a non-Newtonian shear thinning fluid. And so it's quite complex. There's yielding that's involved. And the yielding can, in fact, lead to very small viscosities, which can cause all kinds of problems. And you typically have something like 9 orders of magnitude variation in the viscosity of the rock. But what you see here is a cross-section that shows the Pacific plate subducting underneath the Australian plate. This is this big subduction zone. So these are zones where the largest earthquakes are generated, where one plate is being driven underneath another plate, and friction builds up over time, and eventually, over 100 years, 200 years, several hundred years, the friction is finally overcome, and you get the big uplift that causes a massive magnitude 9 earthquake with a vertical motion. Often these subduction zones are offshore, so these lift up a column of water, which creates tsunamis. And so we're trying to understand this process. But as you can imagine, we don't know what's happening inside the Earth. We can only infer it from observations. And so what we're trying to do then is, in particular, viscosity, so the constitutive law in this case, and in particular the expression or parameters that go into this non-Newtonian law for viscosity, these are unknown. And so what we're trying to do is infer them, so the interior of the Earth, from observations of velocity of the plates. So these plates move at a few centimeters per year, and this shows actually some in black, some of the modeled velocity, and in white, some of the observed ones. And so the inverse problem is to minimize the misfit between these two. Okay. And these surface velocities come from synthetic aperture radar or GPS. So here's another problem. This is a contaminant in the subsurface. We're trying to remediate this. So there's some contaminant that is threatening to contaminate the water supply of a town. You see the contaminant moving towards the drinking wells. And we don't know the current state of the contaminant, so you can think of this as an initial condition inverse problem. We also don't know the permeability of the Earth, so we're inverting both for the initial condition and for the permeability. Unfortunately, there isn't much information. There's just the pressure and contaminant concentration at wells, but we can put in additional wells, observation wells. And that's actually one of the beauties of the Bayesian framework, because it accounts for uncertainty in the inverse solution. Then you can ask the meta question, how do I acquire new observations in order to reduce the uncertainty? All right, so that becomes an optimization problem that has a Bayesian inverse problem as the inner problem. It's really complicated. Okay, so here's a third problem. I'll go more into depth as a case study later on, but I'll just briefly say that what we're trying to do is model the flow, predict the flow of ice in Antarctica. The observations are synthetic aperture radar, so that gives us this velocity everywhere at the surface of the Earth, and we're trying to invert for the boundary condition at the base of the ice. So this is a three-dimensional model of the ice, and the boundary condition is unknown. It could be free slip, it could be no slip, it could be something in between. So we invert for that parameter that mediates between the two extremes. And so these are surface velocities. This is what we invert for, but I'll talk more about this in a few minutes. This is a problem in global seismic inversion. We're trying to understand the structure of the Earth, and in particular, the structure means, what we can learn from seismic waves means the distribution of the wave speed in the Earth, and that's correlated to temperature and even to composition, mineral composition of the Earth. So the observations we have are seismic waves. So nature, lights up the Earth through earthquakes, and we have seismometers around the Earth. This is actually the Tohoku model of the Tohoku earthquake. The waves are propagating, and we have seismometers around the Earth that measure these seismic waves. And we want to take the seismic wave measurements and go backwards through a wave propagation model to infer the structure of the Earth. And you can see this is done here in the Bayesian setting, where the prior is essentially non-informative. We just have you see these in gray. These are point-wise marginals, and in blue is the posterior. And you can see there's a significant concentration. This is a synthetic problem where we put seismometers in the northern hemisphere to see the effect of limited observations. And you can see in the northern hemisphere we learn considerably. The variance is reduced in these point-wise marginals. In the southern hemisphere we learn nothing. This is North America and South America. This is a few kilometers depth. But this is these are all very expensive forward models. This runs on 64,000 processors. One forward model, one earthquake, to just do the forward model, runs for a couple minutes. Well, actually 1 minute on 64,000 processors. Okay. So here's another problem. I mentioned for the subsurface flows, there's very little information because you're gathering it all from wells. But there is an opportunity, certainly in some places, to combine well measurements of pressure and concentration with deformation of the Earth through a poroelasticity model, or more generally a poromechanics model. And the idea is when you're significantly extracting fluid from the subsurface, from an aquifer or from a reservoir, there can be subsidence of the Earth, and that can be measured by synthetic aperture radar. And you can then go backwards through the coupled mechanics and flow subsurface model to infer the uncertain parameters such as permeability. So you can again measure the surface deformations. These are accurate to within a few millimeters through this synthetic aperture radar, and GPS can also measure it at point-wise locations, and then go back and infer uncertainties. Now you need the aquifer has to be fairly close to the surface in order for there to be subsidence. But in the Midwest of the U.S., for example, where there's been drought for many years, the use of the production of extraction of groundwater from aquifers has led to significant subsidence in many areas, as much meters of subsidence. So we can use that information to go back and try to understand the state of the aquifers. Okay, and then finally, Steve mentioned, it's not just big data, it's complex data also. So most of these examples have been one kind of data, one data modality, and that is, and maybe in some cases we had INSAR and GPS, but they're still measuring displacement, surface displacement, and there's one physical forward model that might be coupled. But in other cases, we have completely independent, uncoupled models. In this case, seismic wave propagation and electromagnetic wave propagation. We can employ both to try to understand the subsurface. There's one subsurface, but we can use both data sets to understand different attributes of the subsurface, and we can then ask that these different attributes, we can put priors on the attributes and tell, essentially force them to describe the same model, right? When you have a seismic wave velocity, for example, and electrical resistivity, those are two different properties. The physics are uncoupled, but they describe the same Earth model. So when you have interfaces, when the rock changes from one type to another, when you have layers, those should be the same in both models, and we can put priors on those. All right, so let me say a little bit about what I think are some of the keys to overcoming these twin challenges, or at least addressing these twin challenges of high dimensionality and complexity of the forward model. And the argument that I and many others make is that you have to exploit the structure of the posterior probability. You can't just apply a black box vanilla method that doesn't take into account the map, the structure of the map from parameters to observables. And that structure arises in at least three ways. First of all, low dimensionality. Despite the fact that we have huge data sets, the truth is that often they're informative about a limited number of modes in parameter space. This is a reflection of the opposedness of the inverse problem. And so effectively, the data are giving you information about the model in a reduced number of dimensions. Despite the fact that you might have 1,000,000 dimensions, they're really only at 1,000 dimensions that the data inform, and the rest are filled in by the prior. So if we can exploit that information, and the idea is to do it through low-rank approximations of linearizations of the parameter to observable map, using randomized algorithms that don't require you to form the appropriate operator. All right, so the second one is sparsity. We're trying to find regions of high probability, and here we can employ optimization algorithms. You saw in that slide with the grinder the relationship, the close relationship between optimization, the Tikhonov approach, and the Bayesian approach, in which the log posterior looks like the objective function for the regularized data misfit that you find in Tikhonov regularization. So algorithms that have been developed for the first class of problems, the regularization approach, which exploit the low dimensionality and curvature information, these methods can be used to find these regions of high probability, and then one can seed Markov chain Monte Carlo methods from those regions. So that's a second idea. A third one is to use second order, to use Hessian information. Langevin methods use gradient information to help you explore the posterior, but the idea is to use curvature information, second order derivatives of the output with respect to the input. Now, this is challenging. You've got a large, complex climate code, let's say. You have some output, let's say that Antarctica model. The output of the code is the surface velocity that will be compared with observations of the surface velocity. The input is a coefficient of a Robin-type boundary condition at the base of the ice sheet, and that map from parameters to observables. Now we're saying, oh, we want the second derivative of that. In high dimensions, in 1,000,000 dimensions. So it turns out there are these adjoint methods. Those of you who do adjoints will know this. This is standard. But adjoint methods can give you the gradient at negligible cost, essentially one linearized forward solve. For the second derivative, for the Hessian matrix, it's not so easy. One column of the Hessian is equivalent to the gradient in computational cost. But again, in combination with these randomized methods that extract the low-rank approximation, we have to do only a few matrix vector products. And each Hessian action amounts to one adjoint, one linearized forward, one adjoint solution. And the idea is that there are a few number of these to be done, and so we can effectively use second-order information to help us move in parameter space and understand the anisotropy of the posterior. I'll have a picture to illustrate that. All right, so using these ideas, one can solve Bayesian inverse problems, up to 10 to the 9 state variables and 10 to the 6 uncertain parameters on, sort of 100,000 core supercomputers. But it's very expensive. It's very expensive. The key idea, though, is the number of model solves, the forward model solves, is independent of the parameter and data dimensions. It depends only on the information dimension. So the parameter space, that does not influence the dimension of the discretization of the parameter space, and even the data dimension as well. That doesn't matter. What matters is how much information is contained in the data, how informative the data are about the parameters. Now, you can prove this for simple problems, simple elliptic and parabolic and hyperbolic problems. Linear, in fact, in all cases I know about, linear in the state, nonlinear in the coupling between state and parameter. But numerically, we can observe it, and I'll show you some numbers. We can observe it for all these other cases, that there is a rapid decay in the spectrum of the Hessian, which makes a lot of this exploitation possible. But there's no free lunch, except for today. but in general, you have to pay a price. And that price is they require deeper information from the forward model, such as adjoint-based gradients in Hessian, which require you to go differentiate the underlying PDE or other integral equation, n-body problem, whatever. But they require you to differentiate that model and to solve that in parallel with the forward model. So you have to solve these adjoints and second-order versions, linearized versions of those things. So this doesn't play well with the sort of the modern view of these large community codes that have been developed over decades without this sort of thinking involved. So there has to be a big sort of cultural change in order to get the large community codes and other legacy codes to embed them with gradient and Hessian information. So everything that we've done, we have to write our own forward codes. There's just forward codes, and we embed them with adjoints. There's just no alternative. All right, so here is a little bit of a peek under the hood, just a little hint illustrating how these methods work. This is a vanilla random walk Markov chain Monte Carlo method. So we're trying to sample a distribution that has contours in gray. So it's just 2 dimensions, so it's easy to visualize. And here's an isotropic Gaussian proposal. And if we draw a sample from this and use that as a proposal for Markov chain Monte Carlo, it's going to be rejected most of the time, especially in high dimensions. And so, of course, the challenge is to construct a proposal density that looks like the underlying posterior, but is cheap to evaluate. And so the idea is you can use a proposal that understands to 2 derivatives the structure of this posterior. And so, as I said, we can seed, we can sort of take advantage of sparsity by seeding the optimization from the so-called maximum a posteriori point. And then we can sample around it. But when we sample, we draw samples from a Gaussian that has the Hessian, the inverse of the Hessian as its covariance. And so this is the Hessian, again, of the output of the model with respect to the input. And this requires, inverting H. It requires the determinant of the square root of H. And I just said that, each column of H amounts to a linearized forward model, a linearized adjoint model. So that's the 64,000 or 100,000 processors running for a minute. So that's out of the question when you have 1 million columns of the Hessian. But then, as I said, these Hessian operators, the data misfit portion of them, they admit to a rapid decay in eigenvalues, in reflecting the opposedness of the problem, the fact that the data don't inform all the parameter dimensions. So all of these computations can be done actually in a way that does not depend on the parameter dimension. One can invert H, one can find the determinant of the square root of H in order to compute the acceptance probability. One can draw samples from a Gaussian with H inverse as its covariance. All of that can be done once you've computed the low-rank approximation of the data misfit with just minimal linear algebra after that. And then the low-rank approximation of the data misfit portion of the Hessian is done by solving linearized forward and adjoint problems as many times as the data are informative about the model parameters. And I'll show you an example of that. Okay, so let me say a little bit about this Antarctic flow problem. So this is greatly exaggerated vertical scale. The ice in Antarctica is several kilometers thick on average and several thousand kilometers in extent. And as we all know, it's ice that is on land that has the greatest potential for raising sea level. Sea ice, if it melts, it's not going to change sea level, except maybe in an indirect way because it changes the reflection, the albedo of the Earth's surface. But it's land that's on ice, the ice that's on land, rather. This is the one that has a potential for sea level rise, and Antarctica has 60 meters of sea level rise locked in all the ice. Now, the ice is not going to go anywhere in a short period of time. There have been periods in Earth's history when there's been no ice in Antarctica. But the danger is that the ice, as it flows off the continent and into the ocean, this process has been observed over the last several decades to be accelerating, and certainly in certain portions of Antarctica. And this acceleration is probably due to increased circumpolar currents. So the circumpolar wind has caused greater mixing in the ocean, and that has led to warming in the sub-shelf. So the ice that's on land is this is the ice sheet, and when the ice flows off land onto the ocean, this is an ice shelf. So the waters in certain portions of Antarctica have been warming, and that has caused greater melting of the ice, and that leads to breakup of these ice shelves. These ice shelves play an important role. They buttress the flow of ice from land. So they keep the ice from flowing from land. As these break up, the flow accelerates, and this has been observed. Last couple of decades, in particular West Antarctica, the ice is getting thinner over land, and it's flowing faster. And the fear, if this continues, it can lead to catastrophic sea level rise. And this has happened in Earth's history, 118,000 years ago, at the end of the last interglacial period, so just before the last ice age began. There's evidence that sea level increased over a relatively short period of time, a few hundred years, by as much as 5 to 7 meters. Okay, probably due to a collapse of a large ice shelf. All right, so what we're trying to do then, this represents the boundary condition at the base of the ice. As I said, the ice can be frozen to rock, so there's a no-slip boundary condition. It can be sliding freely because there is fluid underneath, both from geothermal heat flux that's melting the ice and from friction. There are lakes underneath. And in most places, it's somewhere in between. There's some resistance to sliding, so it's not stuck. The ice is not stuck to the rock. There is some resistance to sliding, but it's not sliding freely. And so this parameter, basal friction, represents the resistance to sliding. So we can take these surface observations, this surface velocity, this is from INSAR, satellite radar, and we can go backwards and solve the classical. This is now the Tikhonov regularized inverse problem, and we can find this distribution of basal friction. And actually, it's quite surprising that there's very little resistance deep into the interior. So, so little resistance to sliding, extending hundreds of kilometers into Antarctica. And this is actually this is the cube root of the basal friction. So this is 9 orders of magnitude variation. In the interior, the ice is essentially frozen to the rock. That's what the data are telling us. But out near the coast, it's free to slide. And what you can see here, you can see these ice streams, this fast-flowing ice. This is several kilometers, 4 kilometers per year. This is West Antarctica over here, where some of the greatest flow rates are observed. And even in East Antarctica, you can see that there's fast-flowing ice streams. And not just beneath those, large areas show little resistance to sliding. When you solve the inverse problem through this nonlinear Stokes forward model and through the surface velocity. There's a lot of data. There's a lot of data. The satellite data, essentially on a grid of a few hundred meters, everywhere on the surface of Antarctica, we have velocity, 3-dimensional velocity vector. All right, but what does this tell us? This doesn't tell us about the confidence we have in the solution. We have to go to the Bayesian solution. So this is actually just a Laplace approximation of the posterior. So this is essentially going to the map point and using the inverse of the Hessian to estimate the covariance. It would be exact if it were a linear inverse problem. Here it's just an approximation. But using these low rank ideas, one can then sample, these are samples from the prior, they don't show you any particular structure. These are samples from the posterior, and as you can see, there's little variability in the interior. There's large variability in the interior, but little variability in these fast-flowing ice streams. So what you can, and you can actually combine this into a map of this is the standard deviation, the posterior, and you can see that there's maybe 2 orders of magnitude, 1.5 orders of magnitude, larger standard deviation in the interior than there is out at the ocean. So this tells us, relatively speaking, that we can have greater confidence in these regions that are critical. The inference of the basal friction at the base of the ice sheet, we can have greater confidence in it in many of these regions where you have fast-flowing ice flowing out to the ocean. Okay, so this is I said that often these problems, despite the fact that they have many parameters, actually have little information contained. Lots of data, lots of parameters, but the data don't inform the model parameters in beyond, in this case, a few thousand dimensions in parameter space. So this shows you the spectrum of the inverse of the Hessian. Again, this would be the covariance if it were a linear inverse problem. So this is the inverse of the Hessian at the map point. And this is the spectrum. And as you can see, there's, 8, 9 orders of magnitude decay in eigenvalues over the first 5,000 dimensions for 2 different discretizations of the forward model. So one discretization, and particularly of the parameter field. So the basal friction field, you saw that map of it before. The blue dotted line is 400,000 parameters, and the black line is 1.2 million, and they lie on top of each other, which tells you that once you get to sufficient resolution, the spectrum is not changing. Now, you do still have to have a fine mesh because you don't know where the data are going to inform. As you'll see, there are localized regions where the data are giving you a lot of information. So we can't just say, oh, we'll just use a coarse mesh and then we're done. You still have to have a fine mesh, but then you have to let the data tell you where the action is, and then you use these randomized algorithms to extract the low-rank approximation of the data misfit portion of the Hessian to identify those low dimensions in a way that scales only with the low dimensions. So the number of forward model solves that we have to execute depends only on this dimension, the 5,000, or depending on where you cut 4,000, not the million dimensions. So this actually seems like it's too good to be true because you're in a million dimensions, but this says you only have to touch 4,000 or 5,000 dimensions. And when I say touch, you only have to solve the forward model, actually linearized forward model, in those 4,000 or 5,000 dimensions. And that gives you full information about the behavior of the posterior. All right, so as I said, this does not depend on the parameter dimension. It also doesn't depend on the data dimension because as we refine the mesh here, we also refine the surface mesh. So the surface mesh is the one in which the data from the satellite are projected onto, and the satellite data are much finer, on a much finer grid. So we're picking up more information from the satellite, but we learn just as much about the boundary condition at the base, simply because the map from the boundary condition at the base of the ice, forward solving through this nonlinear Stokes, coupled mass, momentum, and energy, up to give you the surface velocity, that map is, information is being lost from that. All right, so just to give you an illustration of what these eigenvectors look like, I've picked a few eigenvectors from the spectrum. And so this is the eigenvector corresponding to the first eigenvalue. So this is the most informed mode. This is what the data are trying to tell us, and they're trying to tell us that this portion of West Antarctica is most informed by the surface velocity, so the boundary condition in that region. There's the second one, the third one, it goes to East Antarctica. As you can see, these are very localized. They're not like mode shapes of a drum, maybe a drum that has variable thickness, you could say. And as you go to, there's eigenvector 10, 100, you start to see smaller length scales. So there is information on the smaller length scales of this boundary condition coefficient. But there's less information contained. So this is now 2,000. This is the last one, 4,000. So again, there's very little information in the interior, and that's why the variance is so large in the interior. But you see small length scales in regions where the ice is flowing fastest. So it's that fast-flowing ice on the surface. The observations of that are telling us most about the boundary condition at the base. Okay, I have a few minutes left. So still, despite the exploitation of curvature and low dimensionality, in the end you're still doing 10 to the fourth. These are linearized forward solves. So the adjoint involves linearization of the forward model. But this is still quite expensive. And this for Antarctica, all of those computations took about 10 million processor hours. And this is just the Laplace approximation. So the idea is, can we replace these forward models with reduced models? Okay? I mean, this is something that people have thought about for many decades. The most popular reduced model are projection type reduced models, principal orthogonal decomposition. But those are very difficult to establish for nonlinear problems, for nonlinear forward problems, in high dimensions, making them parametric, making them predictive over the million parameter dimensions. That's essentially an open problem in model reduction. And there are other kinds of model reduction. But here, what we're going to do is, all right, Steve told us this morning, neural networks are hot again, so let's give that a shot. Well, we tried it, and of course it failed miserably. You can't, to get a neural network to represent a map from a million dimensions to whatever the surface observations, you get a crazy network, and the standard methods just aren't capable of solving it. But the idea is to come up with some representation, f, that depends on the model parameters, and there will be, in this case, let's talk about a neural network. So these will be the weights and biases of W as the weights and biases of the network. And we're going to train this representation using training data. But what we're really interested in is that this network be predictive. It generalizes well to unseen data. That's what everyone worries about. So what we're going to do is take a Newton-based approach, which really comes from sort of the stochastic optimal control world, where the system that one is controlling, one can think of the neural network as a system that one is controlling. I mean, it's a propagation of information from inputs through many layers to outputs. So can be thought of as a dynamical system, and one can compute adjoints. In fact, that's what backpropagation is, but higher order adjoints as well. The same sort of technology that was used for the Bayesian inverse problem, we want to use it here. Because after all, training a neural network is an inverse problem, and one ought to, in my opinion, approach it as an inverse problem. All right, so what you'd really like to do is you would like to minimize this loss function. So you can think of this as a misfit between the model, the neural network model, and the true, let's say, the Antarctica flow model, the expensive flow model. So we can't evaluate y too many times. So this is a different setting from the usual deep learning setting where you have a huge amount of data. Here, the forward model, we can evaluate a few thousand times maybe, but no more. And we're trying to build a neural network representation to it in a million dimensions. Okay, we want it to be predictive in a million dimensions. And so the idea is that we're going to use training data, but the original problem is we're trying to minimize this loss function over all of parameter space. So this leads to a stochastic optimization problem. We've got some distribution. We care more about some regions of parameter space than others. For example, if we're going to use this reduced model F to do uncertainty quantification, we're going to be sampling, and we care about certain areas more than others. And so what we really have is an expectation with respect to a distribution on the input parameter m. And we're trying to minimize the expected risk. Now, this integral, of course, is too difficult to manage. I have a few slides at the end about some ideas on how to bring in more information, but I probably won't be able to get to them. But the standard thing to do is then to replace the integral with the Monte Carlo approximation. And so we can think of these Monte Carlo points as training points. We're trying to minimize this empirical risk function. Okay, but rather than do stochastic approximations, like what you've heard of stochastic gradient descent, which is very popular in machine learning, we're going to use a sample average approximation. In other words, solve this problem using a Newton-type method. And so some comparisons between these two. Stochastic approximation works with mini batches. rather than use all of the data, because you can think of this as an inverse problem with multiple sources. So for each I, you're sweeping forward through the network, and if you have to do this thousands of times, it becomes prohibitive if you have a very large network that the kind you would need to represent a complex physical model. And so the idea is that you work with subsets of the data, and then you randomly choose these subsets and you cycle through them, and you compute gradients based on this limited data, and you move in this gradient direction. Now this isn't the gradient of the original function. It's an approximation. It's a stochastic estimate of the gradient, and the convergence can be assured under certain conditions, but these methods take huge numbers of iterations. On the other hand, the sample average approximation transforms this stochastic optimization problem into a deterministic optimization problem, which we can hit with Newton's method. But the key idea is that we don't just, there's the standard saying in machine learning is, oh, you can't use Newton methods because they can't handle high dimensions. And the problem, the thing there is you don't actually form the Hessian. So that's we know this from inverse theory. You never form Hessians. You only form their actions in a vector, and you use conjugate gradient methods to solve the resulting Newton systems, and you make use of this low dimensionality, the fact that the data are informative about low dimensions in parameter space. In this case, the data are actually the input-output pairs, and the parameters are the weights of the neural network. Okay? But it's still an inverse problem. And so you get rapidly converging methods, and these methods, SAA, address a number of the difficulties that you can guarantee a descent direction, you can guarantee asymptotic quadratic convergence, if you have sufficient smoothness. It's clear, the stopping criteria are clear, the step lengths are clear, unlike many of these problems with stochastic approximation. Okay, so what is, everyone knows Newton's method. Hessian search direction is minus the gradient, and then we're going to update the weights. But the trick then is that you never form this Hessian. You recognize that it is it's composed of a regularization and a data misfit, and that data misfit portion is the one that admits a low rank representation. And so that's the basic idea. I won't get into the details here, but just let me give you an example. So this is learning a simple elliptic equation. All right, so I'll just show you this one result, and then I'll stop. So we're just trying to learn a simple Poisson equation, but it's in high dimensions, well, relatively high dimensions, 4,000 dimensions. We've done larger, but we compared with a sort of state-of-the-art machine learning method, Atom. And what you see here is testing error. So this is the generalization error. It's decrease, and over here we're not plotting iterations because Newton iterations are not the same thing as gradient descent iterations. The gradient descent iteration is much cheaper. So you have to take into account that Newton does more work per iteration. And so you write everything in terms of how many times you sweep forward through the neural network. And the problem with these Atom methods, there are hyperparameters that need to be tuned. So this is different values of the step length. And what you see is the Newton method rapidly, within a handful of network evaluations, decreases by 3.5 orders of magnitude the generalization error, and essentially matching the best of the Atom generalization errors. This green curve actually does better, but it's not clear where you stop it. So if you go to convergence, then you get a much poorer generalization error. So within a handful of iterations, so several orders of magnitude fewer network evaluations, you get the same generalization error, and then if you let it run, you get maybe an order of magnitude better generalization error. And so and that's the order of magnitude is quite large. Okay, so I'll just stop with the conclusions. So Bayesian inference is an attractive way of solving inverse problems, but if you just use sort of black box tools that don't dig into the structure, into the inside of the parameter observable map, then it becomes prohibitive. And exploiting the structure of this map, sparsity, low dimensionality geometry, allows you to solve or approximately solve some large and very complex forward model Bayesian inverse problems. I should mention, this isn't, the method I talked about is just one. There are a number of other methods that are using Hessian and even third derivative information. But despite all of that, it's still an expensive proposition. Orders of magnitude more expensive than deterministic inverse problems, which are themselves orders of magnitude more expensive than the forward model. And so the idea is, can we use neural networks to construct reduced representations? And I would argue that when doing that, you should take the same approach, view it as an inverse problem, and bring in Newton ideas, low-rank ideas, regularization ideas that come from inverse problems on complex models. And the preliminary results show comparable generalization and several orders of magnitude fewer network evaluations. This has been for somewhat smaller samples. There are some ideas on extending to very large number of samples, but we can talk about that offline. So thank you very much.